Welcome everybody. Today I'm going to talk about single spins, spin densities, average Hamiltonians, and superoperators. These are all important formalisms in magnetic resonance, and I would like to give an introduction into these mathematical basics that are needed to understand the theory of this wonderful field. And the lecture here will be based in large parts on previous lectures given by Stefan Glaser, so he deserves actually most of the credit for this. Looking at NMR spectroscopy, we see that this is a classical technique, and it's a fantastic technique to actually learn quantum mechanics, because when we look at the states that we can excite, then we have tiny little energy differences at the magnetic resonance levels. But when we get out of these closed systems to try to excite a higher spin state in the nucleus, for example, then we need extremely high energies. We need X-rays or even higher energies to go into the next excited state. And so we are very much separated. A small spin system that we can exclusively look at is perfectly suited to quantum mechanics. So now, if we want to look at magnetic resonance, we have several different levels to look at. And so let me give you a brief introduction into the different theories and how they are connected. So we first look at single spins. So we have, in this case, we have wave functions that are typically represented by a vector, for example, here the psi vector. And then we have, of course, a Hamiltonian, which represents the energy function that the whole system develops with. It's called H. And then we have the differential equation that describes the motion and everything that's going on in quantum mechanics. And that is the well-known Schrödinger equation. And that's simply psi dot as the time derivative of the wave function equals minus I H psi, where I already used the magnetic resonance notation that we leave out the Planck's constant h bar. And in this case, any measure A is described by psi times some matrix representation of A times psi, where we use the bracket or bracket nomenclature for describing the joint vector with the left graph and the column vector as psi in the cat form. So we have this single spin, and this is kind of one way to describe the theory. And then we have the problem that we can describe here, in principle, only one spin. And when we have many identical spins, then we have to think of a different formalism. So we have so-called spin ensembles. We have a different function to look at the underlying states. And this is the so-called spin density function, which is just called rho, and it is the dyadic product of psi cat times psi graph. And with this matrix representation, we can go into the Schrödinger equation and then see that this is ending in the so-called Liouville von Neumann equation. which is simply time derivative of the spin density operator equals minus I times the commutator of the Hamiltonian with rho. And as the spin density function represented by a matrix this time, the measure mathematically is described slightly different. It is the trace of A dagger, the adjoint of the matrix A, times rho. And so this spin density formalism has now also developed as a side product two very useful formalisms. And one is the so-called Cartesian product operator formalism. This formalism is used today to derive most complicated NMR experiments. And then we have another very important theory, which is called the average Hamiltonian theory. With which we typically describe nowadays pulse sequence building blocks in what they do altogether. So with these formalisms, we can already describe the vast majority of experiments and what's happening in magnetic resonance. However, there is also relaxation taking place, and this is rather difficult to describe in the conventional spin density operator formalism. So Redfield instead used for his theory the super operator formalism. So super operator, there we have rho dagger in the notation that I will use, and there will be the Hamiltonian super operator, which is H double hat, which is simply the commutator H applied on some operator that will appear afterwards. So we also will have then the so-called relaxation super operator, and that is called gamma, for describing relaxation processes. And this ends up then in the classical Redfield theory, where rho dot is now minus I, the Hamilton super operator, times rho minus the gamma super operator, the relaxation super operator, times rho minus rho zero, where rho zero is the thermal equilibrium state. And of course, also in this theory, we have a measure, and this is then calculated as rho dagger times A times rho. Well, and when we come from this theory and just look at a single spin, then we see we can do a simplification, which, however, historically actually was the first description of magnetic resonance. So we do a single spin simplification. And then we end up the description where we describe the magnetization by a magnetization vector M, which is represented by mx, my, and mz. And these are actually the components of the operators ix, iy, iz. So these are the components of the spin density operator in the XYZ coordinate system, or here as the expectation values of the eigenfunctions of the angular momentum operators. And this ends up in the Bloch equation, which can be written as magnetization vector time derivative equals gamma b cross m minus the relaxation operator r m minus m0, where again m0 is the equilibrium magnetization. And so with this, we have now a really nice overview over all the different formalisms, and we can see now how they all interdepend. And well, we will start now with a single spin description of spins, and then go the way that I was pointing out here. We go then to spin ensembles, then to the superoperator formalism, and the Bloch equation. And when we deal with the spin density operators, we will also have a look into the product operator formalisms. What are the basic ideas behind it? Where are limitations? And also average Hamiltonian theory, a very small example. For all the formalisms that we look at, we also need to have some mathematical basic knowledge. So I would like to write down some mathematical background that is needed. So we will see we have base functions. They're typically called beta 1, beta 2, or we will write them down as their cat vectors. So sometimes we'll say beta 1 and beta 2. Then we have quantum mechanical states. This is described by a vector psi, for example, which is C1 times beta 1 plus C2 times beta 2. And this we then describe simply by a vector, by a column vector in this case, and this is C1, C2, which is the psi cat vector. This nomenclature bra cat bracket we have here. Bra vector is the adjoint of the column vector, so it will be C1 star, C2 star. And this is simply the column vector adjoint. It's the dagger, which my writing looks more like a plus, but it shall be a dagger. And this is just the transposed and complex conjugate of a matrix. So as I say here, the A dagger equals the complex conjugated and the transposed of the matrix A. Then we have the norm of a vector, in this case psi. That is simply the scalar product, which in bracket writing is bra psi times cat psi. The general scalar product is then psi times pi, for example, and that would be C1 star C2 star times D1 D2 as the coefficients of the vector psi, and this is then simply C1 complex conjugated times D1 plus C2 complex conjugated D2. Then I also would like to define the dyadic product which we will need. So dyadic product, and this is psi ket times phi var, and this is then the same vectors, but the first vector is the column vector times the row vector, and this then gives the matrix as a result, not a number. Simply, it follows the rules of a matrix multiplication. So we have C1 D1 star, C1 D2 star, C2 D1 star, and C2 D2 star. Then we have the measures in quantum mechanics. And there we have psi, the developed A, and then we get a psi prime, which is A times psi. And psi here is a column vector, C1, C2. And psi prime is again a column vector, but C1 prime, C2 prime. And that is now the product of the matrix representation of the operator A, which is a matrix here called A11, A12, A21, A22. And this times the column vector C1, C2. And you should be familiar with the matrix product. And let's say we have the matrix C equals the matrix A times matrix B. Then this is nothing else but that the components of CIK are the sum over all j of AIJ times BJK. And when we practically calculate something, then we have a matrix A, the matrix B that we multiply with. We could shift it to the upper, and then we look for each row in the matrix A, where we look at the individual components and we multiply them with the column of the matrix B for every individual component here. And we sum products of each individual component, here in this case, the left uppermost position in the matrix. We also should be familiar with the most simple differential equations. So the most simple ones, first order differential equations, is d over dt of x of t, which is mostly described by the x dot of t. That is, for example, a times x of t. This has a very simple solution. This is simply x of t equals c times e to the a times t. And in this case, the exponential is a times t. And the factor c here originates then from additional boundary conditions. And x may also be a vector or even a matrix, and A may also be matrix. Actually, C may also be a vector or a matrix. Should also mention that the exponential of a matrix is defined by the Taylor series expansion, which is 1 plus A plus 1/2 A times A plus 1/6 A times A times A plus higher components. But when we actually want to calculate a matrix exponential, then what we always do is we take e to the A and then we transform it into some eigenvector picture where we take the exponential and have then v times A times b to the power minus 1. Then it's clear that it is generally true that A and the exponential of the matrix A point in the same direction. So we can actually write this also that system B is, I forgot here, this matrix A that we transform it to is a diagonal matrix. And then we have V times e to the A d times B minus 1 with now the diagonal matrix only in the exponent. And for the e to the A diagonal matrix, we can now write e to the power of the coefficient A11, e to the power of A22 in the along all the diagonal elements, and everything else is 0. So in this case, we can do directly the exponentiation onto the diagonal elements and thereby very easily calculate the matrix exponential, which we will meet later on in the theory. So now we're coming to some basic physics, and we simply take the magnetic dipoles that are in a magnetic field. And if you draw a little picture, then, for example, we have here the magnetic field B, and then we have our magnetic dipole. I will here simply draw north and south part of a typical static magnet. And this magnet here has a magnetic moment, and that is called mu. With an arrow. So this magnetic moment that is directly related to the strength of a magnetic dipole. And in a magnetic field, this results in a torque T, which is simply described by T being magnetic moment cross product with a magnetic field B. So here we have this magnetic field we are in, and then this magnetic field results just in an angle alpha here, for example, with a magnetic field, and this will then result in motion, in a rotation shown by the two red arrows, which will bring the north pole or the magnetic moment in line with the magnetic field. And this motion, this force that is acting here, that can be described by the energy term E, and E is simply minus mu with a scalar product now with B, and that of course is then minus mu times B times cosine alpha, or we can also write it as minus times the mu Z component along the magnetic field if you consider that the magnetic field points along Z. Well, if we look at a real system, then we can imagine, for example, that we have a particle which forms a circular motion where we describe simply the circular motion by the rotational normal. So by this one here, and the motion is described by the angular momentum operator or angular momentum L. It's actually still a classical description, so it's the angular momentum L. And this angular momentum leads then to a magnetic dipole according to the equation Q divided by 2m times the angular momentum operator, which is also written as gamma times L. And here Q is the charge of the particle and m is the mass of the particle that's moving. And gamma, the constant that contains all the necessary parts, that is called the gyromagnetic ratio. So, but if we now go to quantum mechanical systems, then we look at spin, a single spin here. And this is described by a very similar equation. The magnetic dipole is simply gamma times I, where I is the angular momentum of the spin. And then it follows that the energy is described as minus mu times B, as in the classical case. And this is minus mu Z times B, or can also be written as minus gamma times IZ times B, which is expressed in the quantum states by gamma times M times H bar times B, where M is the so-called magnetic quantum number. And H bar is Planck's constant divided by 2 pi. And so with these equations now, we can start. I should maybe add that in this case, there's a quantity that we usually know, which is that the gamma times B together is called the Larmor frequency, which we will use several times in this lecture. So we now look at a single spin 1/2 as the easiest quantum mechanical system. And we know that the spin 1/2 will end up in 2i plus 1 states, which means in this case for spin 1/2, I equals 1/2. We have 2 spin states, and we usually draw them as energy levels. And so we have here the alpha state and the beta state, they typically called, and this order here is true for gamma larger than 0. And these states, well, they're called alpha, beta, but they also have different names. So quite often we find spin up and spin down, or we also find plus 1/2 and minus 1/2. But in common is that they all describe energy levels that are given by minus gamma H bar times B half and plus gamma H bar B divided by 2. And in the following, we will treat these pure states simply as a matrix, or a vector in this case, 0, 1, and this one, 1, 0, for the 2 pure states. Now we can measure the states and different transitions. And if you want to measure what is the population of state alpha, then we can use a simple operator called I alpha, which is represented by a matrix 1, 0, 0, 0. And you can also do the same for the beta state, which is then given by the matrix 0, 0, 0, 1. And these 2 operators are called the polarization operators. And then, of course, we can also have transitions, for example, from spin state alpha to spin state beta, which is described by I minus, and from beta to alpha, which is the I plus here. And I plus is represented by a matrix 0, 1, 0, 0, and I minus correspondingly by 0, 0, 1, 0. And they're called the raising operator and the lowering operator. So now if we have an arbitrary spin state, we can always describe it here as psi equal C1 times alpha plus C2 times beta. And we can make the shorthand notation that this is simply the vector C1, C2. If we have that, then the spin state or the alpha state applied to I alpha, we get the measure, which is simply now 1, 0, row vector times the matrix 1, 0, 0, 0 times the column vector 1, 0. This is 1. So if we have a pure alpha state and we apply the I alpha operator, polarization operator, we get the result 1. That means, yes, the alpha state is populated. Now, if we do the same, if we look at the I alpha state and we want how much of the beta state is populated with the measure, then we apply the alpha state to the beta polarization operator. And in this case, we have 1, 0 times the operator representation 0, 0, 0, 1 times 1, 0. And when we calculate this product, we will see this is 0. On the other hand, if you want to look at the transfer from spin beta to spin alpha, for example, which would be the plus transition, then we have here beta going to alpha state, and the operator I plus would be the corresponding transition state. Then here we see when we do the vector and matrix multiplications, we have 1, 0 times 0, 1, 0, 0 times 0, 1 in this case. And this is indeed 1, as it should be. So we see here fundamental mathematical equations, and with the polarization and raising and lowering operators, we kind of can define the behavior of the spin system really nicely. However, there are other operators that are even more important to us, and these are the so-called angular momentum operators. They are usually represented by the Pauli matrices. And these Pauli matrices are of the form Iz equals 1/2, 0, 0, minus 1/2, which I will write quite often as 1/2, 1, 0, 0, minus 1. And equally we have Ix, which is 0, 1/2, 1/2, 0, which I will write as 1/2, 0, 1, 1, 0. And Iy, which is of the form 0 minus I half, 0, and I will write it as 1/2, 0 minus I 0. Important for the angular momentum operators is that they are so-called Hermitian operators, or also called self-adjoint operators. That means in this case, that the transposed and complex conjugated of the matrix components is identical, and this guarantees that we get real eigenvalues, and in this case then also guarantees that we get actual observable quantities. And simply from the matrix now, we can directly derive simple relations that always hold true, and they can be written down as follows. Iz is simply 1/2 I alpha minus I beta, and Ix is 1/2 I plus I minus, and Iy is minus I half times I plus minus I minus. And I'm sure you can see this yourself by just looking at different matrices. Now let's calculate some eigenfunctions and eigenvalues for these operators. So Iz applied to the alpha state, which is simply 1/2 0 0 minus 1/2 times 1 0. If you apply now the matrix product, then this can directly be calculated as 1/2 times alpha, or simply as 1/2 0 column vector. The same Iz applied to the beta state as the matrix 1/2 0 0 minus 1/2 applied to 0 1. And in this case, we get minus 1/2 times the beta state, or simply 0 times minus 1/2. If you apply Ix to the alpha state, we get 0, 1/2, 1/2, 0 times 1 0. And if we calculate this, then this 0 and 1/2. And this is simply 1/2, but this times the beta state. And then we see directly that Ix has not a valid eigenvalue for the alpha state, as the alpha state turns into the beta state when we calculate it. And so we need to look for something else that is an eigenstate for Ix, and we can simply test Ix and apply it to a state that we call alpha plus beta. And when we apply this, then this is again the matrix 0, 1/2, 1/2, 0, but this time times 1, 1. And when we do the calculation, we simply get 1/2 and 1/2, which is indeed 1/2 times the vector 1, 1. So indeed, Ix has the eigenvalue of 1/2 for the function alpha plus beta. So it's 1/2 times alpha plus beta. And we do a normalization of this vector, because the norm of this vector is actually 2. It's 1 squared plus 1 squared equal 2. And so when we use now the state 1 over square root of 2, 1, 1, then we call this simply the X state. Equally, we can define the state 1 over square root of 2 times 1 minus 1 and call it the minus x state. Just to verify it, we can do the calculation. So Ix applied to minus x, we have the matrix 0, 1 half, 1 half, 0, multiplied by the minus x state is 1 over square root of 2, 1 and minus 1, and that equals 1 over square root of 2 minus 1 half and 1 half, which is minus 1 half times minus x, which proves that minus x is indeed an eigenfunction to the Ix operator. Equally, you can see that 1 over square root of 2, 1 I is the y state, and 1 over square root of 2, 1 minus I is the minus y state. Now with the alpha and beta operators, we have a complete system of eigenvectors that also are the eigenfunctions of the angular momentum operators. And I simply want to point out that here in these equations, that x and minus x are not the negative of the x vector. Minus x is not the negative of the x vector, but it is really only the second component that is the negative of the second component of the x vector. The same holds true for y. And this is remarkable because that means that the wave function cannot be directly added or treated as the negative. It's only the eigenvalues that are the opposite sign. Now when we have the eigenfunctions and eigenvalues, we can also straightforwardly calculate expectation values. And well, here we have alpha iz alpha, which is simply 1, 0 times 1 half, 0, 0 minus 1 half times the vector 1, 0. That is 1, 0 times 1 half, 0, which equals 1 half. As expected, the alpha state applied to Iz gives a finite value, and this is 1 half. And similarly, when we look at the beta state applied to Iz, and we do an equivalent calculation, and I just give the result, then this is minus 1 half. So it is indeed the other energy level, and this is indicated here by this expectation value. If we now apply the x state to Iz, then if you do the math, we find that it is 0. So the x state is not an eigenstate to the Iz operator, and because of that, we end up with an expectation value with a measure of 0. However, of course, if you apply the x state to Ix, do the math, then we get 1 half as a value, as you would expect. But when we apply the x state to the Iy operator, then we find again that it is 0 because the x state is not an eigenfunction to the Iy operator. Now, when looking at the expectation values of the different operators, we need to see something very important, and that is the so-called phase factor. let psi prime be psi multiplied with e to the I phi, where phi is an arbitrary phase, then the expectation value using psi prime times A times psi prime is just e to the minus I phi psi A psi e to the I phi. And because these are just scalars, we can put them out of the bracket notation. So we have e to the minus I phi times e to the I phi times the expectation value psi A psi. And e to the minus I phi times e to the I phi simply results in 1. And because of that, we can state that every eigenfunction is only defined within an arbitrary phase vector e to the I phi. And this, we will see, is not without problems. However, now we want to see how do we use this for calculating the time evolution of the system. So we have the time evolution, and we have the Schrödinger equation. And the Schrödinger equation in its full form is I h bar d over dt psi of t equals Hamiltonian times psi of t. And this is equivalent to the time derivative of psi of t, which is minus I divided by h bar times the Hamiltonian times psi of t, if we bring simply the minus I times h bar to the other side. Now something in NMR spectroscopy, an old physicist's habit is taking place, that people are lazy writing down constants again and again, which are anyway always clear to the knowledgeable reader. So what we will get rid of is the h bar. And because you know the equation E equals h bar times omega, that holds true, we will see that in NMR spectroscopy, all energies are usually given in Hertz. And because we give it in Hertz, well, equations do not contain the h bar anymore. And with this, the Schrödinger equation gets a bit easier, d over dt of psi of t equals minus I h times psi of t. And now if you want to solve this equation, then it's common to make the assumption that the Hamiltonian is piecewise constant, which means here in this case, the Hamiltonian is constant. And then the solution to this differential equation becomes particularly simple, and that is the way that we have psi of t then becomes e to the minus I ht times psi 0, where the psi 0 corresponds to the coefficient c that we discussed previously and which depends on certain boundary conditions that we give. So we now would like to see, of course, how we do such a calculation. And that exercise I leave now for you for the moment, which is like calculate psi of t for the two boundary conditions psi of 0 equals the alpha state or the x state, and then calculate the expectation values for Iz, which is then psi of t times Iz times psi of t, and correspondingly Ix and Iy. The Hamiltonian in this case will be h equals omega 0, so the Lama frequency, for example, times Iz. I'm sure you're having fun solving these equations. Then we reconvene and I will show the results. Solution. For the exercise, we have our psi of t equals e to the minus I omega 0 Iz t times psi 0. And this is e to the minus I omega 0 1 0 0 minus 1 and then 1/2 times t times psi of 0, and that is e to the matrix minus I omega 0 t half 0 0 I omega 0 t half times psi of 0. And now we can take the exponential into the matrix. And so we have a matrix that is e to the minus I omega 0 t half, e to the I omega 0 t half, and then the other components are 0. And of course, times psi of 0. Now we simply put in the starting conditions. For example, psi of 0 is the alpha state. So this is 1, 0. In this case, it's very easily seen that psi of t simply is a vector e to the minus I omega 0 t half and 0. And also for psi 0 equal the x state, which we had as 1 over square root of 2, 1, 1. Then we see that psi of t gets 1 over square root of 2 times e to the minus I omega 0 t half and e to the I omega 0 t half. Now having these vectors psi of t, we can of course calculate straightforwardly the expectation values. So for psi 0 equal the alpha state, we find psi of t Iz psi of t is then e to the I omega 0 t half 0 times the matrix IZ, which is 1/2 0 0 minus 1/2 times column vector e to the minus I omega 0 t half 0. Then if we calculate this gives the vector 1/2 e to the minus I omega 0 t half 0. And when we apply this to the bra vector, then we get 1/2 e to the I omega 0 t half times e to the minus I omega 0 t half. And this, as you can easily see, is 1. So overall, we get the eigenvalue 1/2. When we do the calculation now, psi of t applied to Ix, psi of t, then we have e to the I omega 0 t half 0 times 0, 1/2, 1/2, 0 times the column vector e to the minus I omega 0 t half 0. And this here, it gives column vector 0 and 1/2 e to the minus I omega 0 t half. And so this simply, when we multiply the two vectors here, then you see multiplication gives simply 0. And if you do the same calculation with the y operator, then you see this is also 0. I just see I forgot a 1/2 here. If we now look at the x state, then we see psi of 0 as the x state is 1 over square root of 2, 1, 1. And we also see that psi of t is 1 over square root of 2 e to the minus I omega 0 t half e to the I omega 0 t half, as we showed previously. Then the expectation values are psi of t Ix psi of t equals e to the I omega 0 t half e to the minus I omega 0 t half, because we take the complex conjugate in the bra vector and we have to multiply with 1 over square root of 2. Then we take the Ix matrix, which I write now as 1, 0, 0, 1, 1, 0, and times 1/2 in the beginning. And then we have the ket vector e to the minus I omega 0 t half and e to the I omega 0 t half. And again, 1 over square root of 2. So this, if you calculate, it's not difficult. Then we get 1/4 times e to the I omega 0 t half times e to the I omega 0 t half plus e to the minus I omega 0 t half e to the minus I omega 0 t half. And of course, we can combine pairwise these terms. So this will result in e to the I omega 0 t plus e to the minus I omega 0 t. And now, if you know trigonometric functions, then this equals simply 1/2 cosine of omega 0 t. Now we can do the very same calculation for psi of t with Iy and psi of t. And I will not write it explicitly, but you can do the math yourself. And then you get 1/2 sine of omega 0 t. And finally, if you apply psi of t to Iz, then it becomes 0. So what we see in this exercise is simply that alpha and beta state both will lead to just a constant value. They will stay the same if we have an Iz operator. And on the other hand, if we have an X state in the beginning, then the X state will rotate with cosine omega t plus the Y component sinus omega 0 t. So we'll simply describe a rotation with the Larmor frequency as we expect. But now we calculated it with the exact formalism. Part 1 is done.